As a second lecture of the productivity growth theme, I'll introduce you to the so-called Malmquist index approach. So there is a very large literature on the Malmquist index containing different variants of this theme. So the purpose of this presentation is to give you a general idea of the Malmquist index. And in the next lecture, then I'll go in more detail to the practical application and estimation of the Malmquist index. So let's remind us these difficulties with the common index number approaches or growth accounting approaches as it comes to the prices. So when prices are not available at all, or the price information is not reliable enough, for example, if there is some market failures or government failures, so then a natural approach would be then to resort to this so-called shadow prices, more specifically the marginal rates of substitution of the frontier, or the multiplier weights of the DEA or convex regression approaches that we have considered. And this is particularly then helpful for us to connect to this frontier estimation technique. So rather than using this kind of price-based quantity indices or price-based aggregates when the price information is not reliable or not available, then we can actually use this kind of distance function based approaches. And so to shed light of it, let me first connect to this Fisher index that we have considered before. So firstly, let me point out that this Fisher TFP index that we saw in the previous lesson, we can also write it in more compact manner using this kind of product notations. So remember that we simply take this kind of ratios of prices times quantities. So it kind of sum products of prices and quantities. And we can actually express it equivalently as we have done in this first equation. So in that sense, it's like geometric mean of such kind of output-input ratios using this prices P and W as weights. And in this paper by with Churi Post and Timo Sipiläinen, we then extend this idea of the Fisher index from this price-based geometric mean to the geometric means of the distance functions. So notice now that in this second formula we have simply replaced these output-input ratio weighted by these prices P and W. We have replaced them now with this kind of distance functions D. And obviously the distance functions don't depend on the prices. And here, to be able to do this, it's good to maybe refer back to this classic Chance, Cooper and Rhodes formulation of data envelopment analysis. So recall that this DEA problem of Chance, Cooper and Rhodes also similarly started with this kind of weighted outputs divided by weighted inputs formulation, and then developed this kind of DEA efficiency measure, which we also later found that it's actually equivalent to the output distance function. So here the idea is similar, so that this kind of weighted output per input ratio has actually an interpretation as a certain kind of distance function. So I don't go to the technical details here. You can read them in the paper, but let me illustrate the idea with this kind of following diagram taken from the paper. So let's simply think about the two output settings. So we have output number 1 on the horizontal axis, output number 2 on the vertical axis, and suppose we have two output vectors that we consider. So y superscript 0 is the output in the base period, and then from the base period to target period we have y superscript 1 is this output vector in in the target period. So notice that this output number 2 increases very dramatically, whereas output number 1 increases only modestly. So then we have in the diagram also these two curves which refer to the output isoquants, and then we have also this kind of straight thinner lines that indicate the iso revenue surfaces. So if we measure the distance to the from this, for example, starting from this let's take the target period first. So consider this dot indicated by y1. So the distance to the corresponding frontier would be this from the origin to y1 to the origin to point A. So the distance function, output distance function, measures this radial distance from output vector y1 to point A. And if we use the Fisher index or Fisher quantity index, then given this kind of iso revenue line, then for the base period 0, we would also then we could equivalently measure the distance from this output vector y0 to the same iso revenue line, and so project this y0 from the origin all the way to this point D, which is on the iso revenue line of the target period. So that would be similar to this Paasche index, if I remember this correctly. Then we could also take the prices of the base period and as the reference, as in the last payers index. So we could also then have the distance from the target period output, so output 1 to this iso revenue line of the base period. So we could project from y1 to this point B, and this is the nominator of the second ratio indicated in the formula. And similarly, we can then compare the quantities of the base period, so y0 to the iso revenue line of the base period. So project this y0 to point F. So this example is illustrated in this formula also on the top of this slide. So notice that if these observations are allocatively efficient, so if these projection points on the output frontiers are allocatively efficient, so if these projection points match with the revenue maximizing output quantities, then in fact this shadow price based index is equivalent to the classical Fisher output quantity index. And we have proved it formally also in the paper. So if these input and output vectors are allocatively efficient with respect to the input and output prices of the corresponding period, then we can show that this shadow price calculation of the Fisher index yields exactly the same result as the classical Fisher-based index. So this applies, of course, also to the output quantity index, and also that would make also the price index the same. We could also utilize the shadow prices to make a price index if we wanted to. And so then I've raised here also the question that, okay, what if these two indices differ? If we observe the prices and we can calculate this classical Fisher index, and then we can calculate it with the shadow prices, then which one is more reliable, this kind of distance function based index or the price based index? So I want you to pause for a moment to think about this. Would you rely more on the observed prices or this kind of distance function based shadow prices? So this is perhaps to some extent a matter of opinion. I want to remind at this point also this Solow model that we considered in the previous lesson. So remember that Solow started by deriving his equation from the production function, and these weights W were output elasticities of labor and capital, respectively. So in that sense, Solow starts implicitly from the shadow prices and then uses the observed market prices as the proxy for those. So he assumes then that this price information matches with the shadow prices rather than the other way around. Of course, to have these shadow prices, we need to estimate. So then the question is more that, okay, do we rely more on our ability to estimate these shadow prices from quantity data, or do we rely more on this observed prices? And in my mind, there is not really any clear-cut preference to one or the other. It depends on how reliably we can estimate those shadow prices. However, this shadow price Fisher index is not really the mainstream approach to using the shadow prices in productivity analysis. So there is very closely related but slightly different approach that is the very standard approach in the productivity literature, and it is commonly referred to as the Malmquist index. However, I find it intuitive to connect this to the Fisher index, so I started from this shadow price Fisher index. So similar to this, what I had the shadow price Fisher index, the Malmquist index also uses the distance functions to measure productivity. So these distance functions D are in the same way the output-oriented radial distance functions that are used in the previous example. And notice that it also is similar to this Fisher index in the sense that it uses a geometric mean. And this geometric mean refers to the distance functions evaluated against the technology of the base period 0 or the target period 1. So this technology, you can read it as is in the superscript of this D. So D superscript 0 refers to the fact that we use the technology of the base period to measure the distance, and D superscript 1 refers to the use of the target period technology as the benchmark to which we measure the distance. Notice that when we have these two ratios here, we have these always the input quantities x and output quantities 1 measured in the target period in the nominator, and the base period 0 always appears in the denominator. So what then changes in these two ratios is only that we use the technology of the base period or the technology of the target period. And since we do not have any clear preference between the technology of the base period or the target period, so we use similar argument as the Irving Fisher in the 20s, that we take the geometric mean of these two ratios. So that is the standard definition of the Malmquist productivity index. So this kind of productivity index was first introduced by Caves, Christensen, and Diewert in a 1982 paper. So they attribute this idea to Swedish economist, I think his first name was Sten, if I remember correctly. Anyway, Malmquist, whose work was in the 1950s. And I've read this original paper of Malmquist. So Malmquist is actually measuring distance and in the commodity bundles of the consumer. So it's in the consumer setting, and he measures difference between some indifference curves of the consumer. And in my mind, at least, these distances from the indifference curves are completely analogous to this distances of the Shephard's distance function. So Shephard was using the same kind of idea in the context of production, and this is also how it is usually formulated. So we use the Shephard distance functions, and Shephard's work was also, I believe, in the same year as Malmquist also. So in my mind, at least, the term Shephard index would be more appropriate for this kind of development. For some reason, Caves, Christensen, and Diewert adopted the name Malmquist index, and this has stayed ever since. But in my view, this just naming convention just also illustrate that sometimes these names after some person are not really always so clear cut or without possibility to debate. Anyway, if I would start to unilaterally call it a Shephard index, then nobody would understand what I'm talking about. So I also use the term Malmquist index, even if it's in my view a little bit misleading. So it's certainly misleading to cite the Malmquist paper for this particular formula that I have presented here. And one more point also to mention is that always in this Malmquist type developments, we use the constant returns to scale benchmark technology, because remember that in this kind of single output, single input case, this index should boil down to simply the ratio of output input ratio, and to preserve that property, we always need to have constant returns to scale benchmark technology, so that in the single output, single input case, this boils down to the classical productivity index. Okay, so what would be then the connection between the Malmquist index and the shadow price Fisher index that I was talking about? So I have illustrated it here, and I have here used this kind of red lines to simply indicate where these two indices differ. So on this slide, you can see also how in this example the shadow price Fisher index would be calculated. So that is this F subscript S, and corresponding Malmquist index is M. So notice that whereas in the shadow price Fisher index we took these shadow prices of the base period and target period, and then extended these facets, so that we had this kind of ISO revenue lines. So we projected this base period observation Y in period 0 to all the way to point D in the target period. So in contrast, in the Malmquist index, we do not use this ISO revenue line, we use the output isoquant. So the Malmquist index would then project to the point E when we evaluate this base period observation relative to the technology of the target period. And in the same way, in the shadow price Fisher index, we use this point B from the ISO revenue line to compare the outputs of the target period to the base period benchmark. So now in the Malmquist index, we do not use point C, we use point C rather than point B. So we then project this output Y1 not to the ISO revenue line, but to the output isoquant of the base period. So indeed, those two red line segments of these radial projections, those indicate the gap between the shadow price Fisher index and the Malmquist index. But otherwise, the rationale is completely the same. So perhaps one of the important reasons for the great popularity of the Malmquist index has been that it's possible to decompose the Malmquist index to the components of capturing the technical change and efficiency change and scale efficiency. So I have here, on this slide, I have stated this decomposition first and these three components formally. So this might look a little bit intimidatingly technical. Don't worry, I will briefly walk you through the interpretation using again this kind of two output situation. Regarding the literature, I want to mention that this decomposition is usually attributed to this American Economic Review article by Rolf Färe, Shona Groskopf, and their co-authors Norris and Chang. I forgot their first names. So this is perhaps the most best known paper of Färe and Groskopf. They have published several hundreds of papers on productivity and efficiency, but this is definitely this Malmquist decomposition is perhaps their best known, most widely known work. However, it's also interesting to note that there was similar decomposition was proposed already somewhat earlier by Nishimitsu and Page in the Economics Journal. However, this Nishimitsu and Page decomposition doesn't use the term Malmquist index because, well, if you remember when Christensen and Diewert introduced it, it was around the same time. So this term Malmquist index was not even invented yet when Nishimitsu and Page decomposed productivity. So they refer to Farrell's 1957 paper. But essentially, they have also the same idea of decomposing the use of these kind of distance functions or Farrell efficiencies, if you like, and measuring the technical change and efficiency change components in a very similar way. In my view, it's a bit pity that this Nishimitsu and Page paper doesn't get enough credit as it would deserve in this context. So, true original component of this Färe, Groskopf, Norris, and Zhang decomposition is this introduction of the scale efficiency part. So let's first of all try to get more intuition. So notice that from this decomposition, it's worth to note that this Malmquist productivity index is the product of the three components, which are the technical change, this PF change, so it's pure efficiency change, and SCH is a scale efficiency change. So let me then walk you through these three components in more detail. Firstly, what is efficiency change? And I use the same two output illustration that we have considered before to see what is the change of efficiency. So we can simply measure the distance to the frontier, and we can take it in the base period, and we can use it in the target period. So by taking this ratio of how much there has been this efficiency and the base period and target period, comparing the two, we get this measure for how much efficiency has changed. So then we have the technical change, and there the idea is to measure the gap between these two output isoquants. So firstly, if we look at the base period quantities, so we could then measure the distance between these two output isoquants from the point of view of the base period observation y0. So notice that if we then project radially from the origin to this through these two isoquants, then this distance between points F and E on these two output isoquants would then be a measure of how far this frontier has shifted from the base period to the target period. In the same way, we could also look at then what is this distance from the target period point of view. So if we take this output quantity y1 and project it radially to the two output isoquants, so this distance between the points A and point C, that would be also a measure of how far these two different isoquants are from apart. Of course, there would be arbitrarily many different potential projections, but the idea of measuring this technical change component is then to use this base period perspective and the target period perspective. So measure this length of these two red lines in relative terms, of course, and then take the geometric mean of the two. So that's the technical change component. The scale efficiency would be, of course, similar to this. So scale efficiency is then comparing the if I take a couple of steps back. So here, this bottom part, it's just using the distance functions relative to this variable returns to scale and constant returns to scale, technology. So that's how then this scale efficiency change is measured. So I mentioned that the scale efficiency component was first introduced by Färe, Groskopf et al. But that also has attracted quite a lot of critical debate in the literature. And the first authors to criticize this scale efficiency component were Ray and Desli. A few years after this article was published, and this Ray and Desli critique also came out in American Economic Review. And they point out that in this decomposition, technical change is measured using this constant returns to scale benchmark technology. But Ray and Desli find this somewhat counterintuitive. So they prefer to measure technical change using the variable returns to scale technology, which they think of as more appropriate for measuring the technical technical change, technical progress. But then, of course, changing this benchmark technology then obviously also affects the other components of the efficiency change and scale efficiency change. So there has been quite a lot of debate about this. What is the most natural way to decompose these three components? It seems to me that every notable author in this field has their own favorite decomposition, and because this kind of beauty of one decomposition, it's mainly relies on the intuition that for one author, one decomposition looks completely natural and intuitive. For another author, it's the different situation. So because there is not some clear objective standards, what is appropriate and what is not, then this debate probably will be never satisfactorily resolved, as far as we rely on the intuitive appeal. Of course, I happen to have my own favorite decomposition as well, so I conclude by briefly discussing that one. So in my mind, it's interesting to connect to the classical index theory approaches. So I have started from the Fisher TFP index, and in this work with Timo Sipiläinen, we managed to decompose the Fisher index to the 5 components, which are technical efficiency change, technical change, scale efficiency change, allocative efficiency change, and so-called price effect. So naturally, when we talk about the Fisher index, then the prices become an issue, and there's potentially the allocative efficiency change should be also considered. But then the price effect also is that sometimes this prices become more favorable or less favorable from the producer's point of view. So this price effect captures that aspect. And in my view, an appealing feature of this our decomposition is that, for example, we do not need to specify that do we take an input orientation or output orientation. So, for example, for the change of the technical efficiency, which is indicated in this equation 22 and the parts of 22a and 22b. So in our decomposition, we can actually use the input-oriented distance function, and we can take the output-oriented distance function and use the geometric mean of the input and the output orientation as our measure of efficiency change. And similarly also for the scale efficiency and allocative efficiency. So I believe that there are many appealing features in this decomposition. Also, of course, if we do not have the price information, so I started this lecture with the motivation that perhaps price information is not available or it might be unreliable. So we also have this shadow price Fisher index. So these last 2 components of equation 21 would be then simply disappearing. If we do not have price information, we cannot also measure allocative efficiency and price effect. But then we could also use this decomposition to decompose the shadow price based Fisher index. And in my view, this decomposition actually addresses this many of the issues in this debate of the Malmquist index, because there is not any kind of component that doesn't have any meaningful interpretation. So, and it also doesn't depend on the input or the output orientation, which is also a nice feature. So, unfortunately, this decomposition has not really attracted a lot of attention or applications, but I hope that in the future somebody perhaps finds and takes it more seriously. So in the next lesson, then I will discuss more practical details of how to apply this Malmquist approach. So far we have only considered at the theoretical level of how to decompose productivity change using the distance functions, but of course to apply the Malmquist index and related approaches such as the shadow price Fisher approach, we need to estimate the distance functions. So in the next lesson I will then discuss how we can do that in DEA or parametric methods or using the stoned approach.